Hi, ladies and gentlemen. Welcome to our last topic for the course. This is our first lesson in Markov matrices. And what we're going to do is take a look at exactly what transition matrices are and the types of situations where transition matrices and Markov matrices are applicable, along with answering some of the fundamental questions associated with these systems. So let's take a look. First of all, the excerpt that I've given you is from my text. It's section 5.4. Strang doesn't have a dedicated section where he addresses Markov matrices. So this is just a cleaner and easier way for us to go through this. And what I'm going to do is highlight some of the content that's in here along with some of the examples. So now that I've got my highlighter turned on, definitely recommend, right? There's really only about 7 pages, 8 pages of content here. And I recommend that you read through this, although I will, like I said, highlight some items as we go. So to start, we're going to take a look at situations that really are defined for use with Markov matrices. So the example here is we have a rat moving around in this contraption here where we have 4 rooms, rooms 1, 2, 3, and 4. And the black arrows show the paths to move between those rooms. And as this notes, right, one of the arrows like this means that for one of the turns, one of the steps, the mouse just stays in room 1. So for example, a mouse in room 1 can stay in room 1, or it could move to room 2, or move to room 3, or move to room 4, as opposed to a mouse in room 2, which really only has 2 options. It can stay in room 2. There's no path to room 3. There's no path to room 4. It could go to room 1, and that's its only other alternative. So the discussion down here has to do with calculating those probabilities, and that's really what's behind all of this is random motion between different states. So that's one of the important words that we want to throw out, right, is the idea of states. And these items here are states that we will use as a means of writing down the transition matrices. So here's the transition matrix that goes with this problem and an explanation of how this goes. Let me point out the key fact for setting up these transition matrices. It's right here, right? We are calculating the probability from the row states to the column states. And let me show you specifically with an example what I'm talking about here. So we have 4 states. We have the states are the rooms. We have rooms 1, 2, 3, and 4. And what I'm doing is setting this up. I recommend you do this every time when you're building a transition matrix. It helps to keep things straight, and it helps make it quite easy to fill out the transition matrix. There's a difference between general transition matrices and Markov matrices, and we'll talk about that a little bit later. So the whole idea is we're going, and let me just highlight again, right? We're going from the row states and we're going to the column states. So the entry that is here is the probability of going from 1 to 1. So in order to calculate that, we need to figure out what all the possibilities are for us when we are leaving, going from room 1. And as we discussed previously, the options here are to stay in 1, go to 2, 3, or 4, and they're all equally likely. So the probability of going from 1 to 1, in other words, staying in state 1, is 1/4. And similarly, it's 1/4 for each of these transitions, going from 1 to any one of the other items, rooms, has to be the same. Let's do one more example down here. Look at room 4. So the possibilities for room 4, we could stay in room 4. That's one possibility. We could go to room 3. We could go to room 2. We can't go to room 1. There's no arrow that leads us back from room 4 into room 1. So there are only 3 possibilities. So our divisor is 3. And what we look at then is, again, going from 4 to 1, that's probability 0. There's no way we can make that happen. The other probabilities, 4 to 2, 4 to 3, 4 to 4, are all equally likely, which means these are all probability 1/3. And then you can read through all of the content that's here to figure out how the rest of this is constructed. This is just an example of how we do this. So there are a couple of very common questions that we're interested in answering, and they're listed here, questions A, B, and C. And basically what it comes down to is we would like to know what the probability is from transitioning from one state to another state in a certain number of steps. So that's another vocabulary word for us, is this whole idea of steps. So Markov processes have a couple of fundamental features associated with them. One of them is randomness, right? We are randomly moving around. The other one is we have no prior knowledge impacting those probabilities. So it doesn't matter how we ended up in the state we are currently in. The probability of going from where we are to one of the other states is independent of how we ended up in that state in the first place. And so some of the common questions are outlined here, right? Probability of getting from one state to another in a certain number of steps. This one, B and C, they both have to do with distributions of the initial objects. So if we have a set of rats in our maze here, in our system, it's not really a maze, and we start with 100 rats in room 1, after 5 steps, what's the expected distribution of rats throughout all the rooms? Those are the types of things that we'll be looking at for questions B and C. All right, so let's start with question A. That's where this begins, this conversation. And what we want to do is we want to understand, which I think is most easily shown using the transition matrix. And remember, we're going from rows to columns. So the way we think about this, we're going to think about this as we have rats in each of the states, and we're going to line those up as a row vector. So let's say, for example, we have a rat that is in room 2. And the question is, what's the probability that that rat has moved from room 2 to room 4? Well, when we do this matrix vector multiplication, we're going to end up with a row vector, and that row vector is going to give us the distribution. And we can see very easily what that's going to be. When we take that row vector and we sweep through, we're just going to end up with 1/2, 1/2, 0, 0. So the probability of the rat going from the second state to the fourth state is 0, at least in one step. What if we do another step? Well, then what we're really doing, very similar to the map program, we're going to continue to apply the transition matrix recursively. So we're going to take this output after one step, and that becomes the new input. We have 1/2, 1/2, 0, 0. Those are the probabilities of where the rat is after one step. And again, we're going to multiply. And so let me just copy this, and I'll paste it down here. So we're just going to apply the transition matrix again. So this will be the probability after 2 steps, because every step is another application of the transition matrix. So when we do this, we're going to take half of the first row and add it to half of the second row. Let me fill that out. So these are the probabilities with, this is the set of probabilities with this as our initial set of initial states. And so what we can see is the rat going from room 2 in 2 steps to room 4, the probability is 1 in 8. And I can read off all the rest of the probabilities. The probability of going from room 2 over to room 1 is 3 in 8. The probability of being back in room 2 after 2 steps is 3 in 8. The probability of being in room 3 after 2 steps is 1 in 8. So this whole idea of how we're doing this is actually captured with matrix multiplication. So we get the same answer if we take the initial position of our rat and we multiply by p squared, that's going to give us the resulting vector that we have here, the 3/8, 3/8, 1/8, 1/8. And if we want to know the probability of where the rat is after 10 steps, that's just applying the transition matrix 10 times. And what we're going to do then, and we can kind of see how this is going to work out, what we have is transitioning from one state to another in 10 steps. What we're going to have is, for example, I and j, and this is a number. This is a specific value in the matrix p to the 10th power, and this is the probability of transitioning from state I, the row state, to state j in 10 steps. And that's explained throughout, right? So as you read through this, this is a specific example, but then it continues on, and you're going to want to read through all of this to understand that, yep, this is the result. And ultimately, we end up with exactly what we just said right there. We can find the probability of transitioning from any state to any other state in a certain number of steps simply by raising the transition matrix to the appropriate power. Okay, so the next question has to do with the distribution. And so we introduce a vector here, which, and a little bit of notation. And what this notation tells us is this is similar to what we had. We have our vector, which was one rat in state 2, which is the second room, and that's equal to a vector. It's transposed, because we always want to think about vectors in terms of columns. So that's transposed, and then I use square brackets here to say what step it's at. So step 0 is the initial step. And so what you see written here, this is R at 0 is, and then whatever the initial distribution is, in this case, it would be 0, 1, 0, 0. And that's how we represent where the rats are in the process. And of course, it's whatever items there are that are in our system that we're modeling with Markov. So there's a conversation here about how we are going to look at the distribution, and really it's just applying the probabilities of a certain number of steps and taking that and multiplying by the initial distribution of whatever our objects are. In this case, we're talking about rats. But let me show you, first of all, so the examples we were doing is we were taking R transpose times P at some level, for example, 0, and we're getting out R transpose, remember, because they were row vectors, at time 1. Well, like I said, we want to use column vectors, so we're going to take this entire problem and we're just going to transpose both sides. And we're going to rewrite this so that we end up with R being a column vector. And we can see how this is going to work out when we do the transpose of both sides. This will become P transpose. This vector will be transposed. And remember, we do the transpose of the product. We swap those. And this is at step 0. And that's going to be equal to the distribution at step 1. And so, as we demonstrated, if we take P transpose and we square it and we multiply by R0, that's going to give us R at step 2. And this is the recursive nature of these transition matrices. You know already from previously in the class, taking that transpose and squaring it is no different than taking the P matrix and raising it to a power and then transposing it. We generally are not going to do that. That's fine. We're generally going to work with the transpose. And again, the reason that we're using the from rows to columns is because that's how the OR312 class does it and how most people do it. Strang does it the opposite, but we're not really using Strang's textbook for this topic, so it doesn't matter. The little bit that he talks about Markov matrices isn't really germane to our conversation. So we're doing it this way so that we match up with the OR312 way of representing from the rows to the columns. And that will become more clear as we look at Markov matrices. So this process, and this is just a demonstration of how we have the distribution at the K step is just like we said, P transpose, the transition matrix transpose raised to the kth power multiplied by the initial condition vector. So you want to read through all of this material. It's easy to understand what's happening once you look through this and do some examples. And then this is just a list showing you what the probabilities look like as we continue to apply the transpose. And a really important part of this is as we raise this to higher and higher powers, take a look at this matrix right here. This is P transpose raised to the 20th power. And what do you notice about all of the distributions here? Right? Remember, this is transpose, so the distribution is the columns instead of the rows. And you can see that the distributions are the same regardless of where we started. Think about what this means for a minute. We have P transpose to the 20th power. If we multiply that by any starting, so we start with the rat in the room 1, then multiplying by 1, we're going to end up with this 0.1818 and 0.2727, and it's another 2727, and then finally 2727. These are the probabilities of where that rat is going to be located after 20 steps. Well, but here's the point. It doesn't matter whether the rat started in the first room or the second room or the third room or the fourth room. The probabilities are all the same. All of the initial transitions have been washed out to the point where the probability now of moving around the system is equally likely independent of the starting position. So then the answer to question B is, what happens if we have 100 rats that start in one of the rooms? And we want to know where the rats are after, and let's take a look at this matrix here. This is after 3 steps. So what we're going to do is we're going to take P transpose raised to the 3rd, and we're going to multiply this times the fact that we started with 100 mice or rats in the first room. So of course, on the first step, then they move around. And the probabilistic distribution of the rats after the first step, because it's equally likely to be in every room, is that there are 25 rats in every room. That may not be the case. In fact, it probably isn't the case because those are just probabilities. But that's the likely distribution or the expected distribution of the rats after 1 step. So after the second step, then those 25 rats in each room have probabilities of moving to the different rooms. And this is what taking the product of the transition matrix transpose with itself is giving us. And so we can see at the end that the distribution of the 100 starting in room 1 is going to look like 100 times that there, which is almost the equilibrium distribution, even after just a couple of steps, because this is a pretty small system. But we're expecting 18.2 rats to be in the first room, 27.3, and then 27.3, and 27.3. And of course, I've rounded off, and there's no such thing as fractional rats. These are just the probabilities. So these are the expectations, but the reality is that we have 18 to 19-ish, 17-ish rats, or because it's probability, it could be no rats in the first room. But this is just where we're expecting that distribution of rats to be after 3 steps. That's the answer to question B. And it really kind of moves into the answer for question C as well. This is an important piece associated with, and again, as you read through this, you'll see the flow of what's happening. Here's an example specifically having to do with where we've taken the 100 rats, and instead of putting them all in room one, we've distributed them for a start in each of the 4 rooms. So we start with 25 rats in each of the 4 rooms. And then where are they after 20 steps? And the expected number of rats in each room is given by, of course, p transpose to the 20th power times the initial. But what you'll notice is this is the whole idea right here of equilibrium. So let me highlight this. This is the idea of the equilibrium, which is that the 21st step, it's almost the same as the 20th step, right? Understand the equilibrium does not mean that we have 18 rats in the first room and 27 or 28 rats in the second and third and fourth rooms, and they just stay there. It's not steady state, it's equilibrium. The 18-ish rats that are in room one are going to, 1/4 of them probabilistically are going to go to room 2, and 1/4 to room 3, and 1/4 to room 4, and 1/4 are going to stay. And then rats from the other rooms are going to move around as well. So it's an equilibrium. At the end of the step, we expect there to be the same number, but it's because they've all been switching locations. All right, so let's talk about Markov matrices. We've been talking about transition matrices, and Markov matrices are transition matrices, but they're transition matrices that have specific characteristics about them. Before we get to that, let's look at the term Markov chain. Right? So the Markov chain is just the repeated application of this Markov matrix. Right? So we have some transition matrix, and it's exactly what we've been talking about. So after one step, right, we would take our initial distribution and we would get the distribution after 1. This is, of course, p transpose. And we can then, for the next step, we would apply p transpose again. And so we have this chain, which is giving us the state after 1 step and then the state after 2 steps. So we have our initial distribution and then our second and our third. And again, we can think of it just as probabilities. We have 1 rat moving around, and these are the probabilities. And this is this chain idea of these continual applications of the transition or the Markov matrix. Okay, so what makes a Markov matrix? These are the same things as the transition matrix. Let me highlight them here. So first of all, of course, the probabilities are always non-negative. Probabilities are values between 0 and 1. They have to be between 0 and 1. All the entries in our Markov matrix, same with the transition matrix, across a row have to sum to 1. So let me bring up the mouse transition matrix. All right, and of course by mouse I mean rat. So this is the rat transition matrix, and what you'll notice is that the sums through each of the rows are equal to 1. That's not true for the columns, right? This column sums to 3/4. The other columns all sum to, it looks like maybe 13/12 or something like that, right? They don't sum to 1. The rows have to sum to 1. And the reason that's true is because we are going from the row states to the column states. And when we go from somewhere, the rat has to go somewhere. It has to end up at one of the other states. It has to. And so because of that, what we know is these probabilities have to sum up to 1. Because the rat's going from state 1 to somewhere, or the rat's going from state 4 to somewhere. And so those probabilities across the rows have to sum to 1. That's another condition for a Markov matrix. So the last condition is, and this is the one that's a little bit more difficult perhaps to understand, but what it says is that when we are taking our P or P transpose, it doesn't matter, and we're raising this to higher and higher powers. So we're building our Markov chain. What it says is that there has to be some K, there has to be some number of applications of moving around the system such that all the probabilities are non-zero. We have to be able to get from any state to any state somehow after some number of transitions, after some number of steps. We have to have gotten from any state to any state. That's a big requirement that applies to Markov matrices that does not apply to transition matrices, and we'll see that in just a minute. Okay, so the Markov chain. This is the formal definition for the Markov chain. We have to start with a Markov matrix. And then what we're going to do is the probability, of course, of moving, this is the answer to question A that we already talked about, the probability of moving from state A or state I to state J after K steps is given by this item right here. This is the answer to B, which is the expected distribution, the expected number of objects at state J after K steps is equal to this. So it's the initial distribution, and then we have K transitions, and this is the distribution that we end up with after K distributions. Okay? So these are all associated with the Markov chain. There's one more really important result right here, which basically says we can't lose objects and we can't gain objects. So the number of objects, and that's what the capital N stands for, the number of objects after K steps is the same as the initial number of objects. We can neither gain nor lose objects. And then finally, there exists a steady state solution. If we have a Markov matrix, there exists a steady state solution, which is the eigenvector of the transpose of our Markov matrix, which has an eigenvalue of 1. And that will be part of what you explore, these eigenvalues and eigenvectors, as you're doing some of the problems. So here's where I recommend that you spend your time after you read through to get a good handle on what we're talking about. Here is what I call the rainy day game, right? It's a very simplified version of something like Candyland. And we're moving from the storm cloud, and we're rolling a die, and we're moving towards the sun. We're moving from the storm to the sun. And the 10-sided die has 1 heart, 2 circles, 3 hexagons, and 4 triangles. And whatever you roll, you move to that next object. So if I'm here and I roll a hexagon, I go all the way up to the hexagon. And the only caveat to that, of course, is if you roll a heart, you have to even go back to the heart. The heart is a state that you have to go to if it shows up on the die face. So what we do is we build a transition matrix. That's what we have here. And remember, when you're building these, you want to make sure that you write down what they are. So let me go back so I can look at the graphic here. This first state is the storm cloud. And then this is the first hexagon. This is the first triangle. This is the first circle. This is the heart. And then we have the second triangle. And we have the second hexagon. And we have the second circle. And we have the sun. And those states match, of course, down the rows as well. And we just label those. So we have the storm cloud, hexagon 1, all the way down to the sun. And that helps us track, as we're building this, the probabilities of moving from one state to another. This is a transition matrix and not a Markov matrix. And the reason it's not a Markov matrix is because it has a situation where we don't satisfy that third condition. I can't get from any state to any state. And we can tell that just by looking at the system. Once we leave the storm cloud's not represented on the die. We can never go back to the storm cloud. So there's no way to get from the heart to the storm cloud. Similarly, there's no way to get from the sun anywhere else, because once we reach the sun, the game is over. So these states have specific names. They're called an absorbing state and a generating state. The generating state as you can well imagine, is the place where we start, and the absorbing state is the sun. That's where we get absorbed and we can't leave. All of that is described in here, and you want to take a look through and make sure that you have all of that down. Okay, so read through that, and then definitely worth your time to look at these questions. These are very common types of questions that will be asked for Markov um, problems. And then the solutions are all down here. And then finally, the last question is, how do the answers to the first four questions change if we change one of the triangles to a heart? Well, that changes all the probabilities, and we have to come in and rebuild our transition matrix. So this is a different transition matrix than we answered the questions with the first time. Also included in here is the umbrella example. You don't need to worry about that. This is a kind of a next level of difficulty that exceeds what we're doing in this class, because we're only spending 2 days just to give you a brief introduction to the application of linear algebra to Markov matrices, where we represent these transitions as probabilities in a matrix, and then we look at the eigenvalues and eigenvectors. So don't worry about the umbrella problem. You can read through it if you want, but that's not required. And then there are some practice problems down here, although we have a lot of problems that we'll be doing in class using worksheets. So let's pull up the questions for today. These are the questions that we have. And these questions are associated with just looking at different ways to transition around in a setup that's similar to what's in the text, but a little bit different. And then understanding what's required here to make Markov matrices. And then finally, a situation where you're going to basically answer question A. So that's it. We'll have another video that looks at some specific examples. Looking forward to seeing you in class. Thanks.